네, 지금부터 Asset Pricing Theory 수업에 들어가겠습니다. 오늘은 그 첫 번째 수업으로서 Asset Pricing Theory를 이해할 수 있는 데 필요한 수학 그리고 기본적인 마이크로 이코노믹스에 대한 강의를 먼저 하도록 하겠습니다. 이번 강의가 끝나면 수학과 경제학에 대한 어느 정도 백그라운드가 갖춰서 그 다음에 나오는 내용들을 보다 더 쉽게 이해할 수 있을 것입니다. 강의는 영어 강의이기 때문에 주로 영어로 하고 중간중간 어려운 개념이 있을 때마다 한글을 섞어서 쓰도록 하겠습니다. 하지만 한국말을 이해하지 못하시더라도 수업을 따라가시는데 큰 어려움은 없을 것입니다. This is the first in the series of asset pricing class. So in this lecture, we will go over the basics of economics and mathematics that is required to understand future lectures in asset pricing theory. After this class, you will have necessary background to understand the basics of asset pricing theory. Let me share the screen. Okay, hold on one second. So to understand this lecture, I strongly recommend you to read the first chapter of Campbell, Financial Decision and Markets. 캠벨 책의 첫 번째 챕터를 보면 여기 있는 내용들에 대한 보다 더 자세한 설명들과 보충적인 내용들을 알 수 있을 것입니다. The first concept you need to know is conditional information. What is conditional information? That is the set of information that is available to investors at time t. And we will denote this set of information as FT. So FT is the set of all possible information available to investors at time t. 즉 FT라 그러면 오늘 현재까지 보통 T is usually the current time, right? T is usually the today. So FT stands for the set of information. 인베스터들이 신문에서 알 수 있는 것들이라든지 시장 상황에서 알 수 있는 것들이라든지 모든 인포메이션을 다 FT라고 표시를 하겠습니다. Now, what is FT0? FT0라 하면 FT0 means the set of unconditional information. FT0는 쉽게 말하면 상수들의 모임입니다. 상수. 그에 반해서 FT는 어떤 time t에 알려져 있는 ZT. So FT is the set of information that can be represented as ZT. For example, the ZT can be something like temperature today. Okay. Whereas when I say the constant or 상수 that is in F0, that will mean that, say, average temperature of all time, which by definition is a constant. So this set of constant is known, is included in the set FT. And as time goes by, today's information set is going to include all that is known in the past. So that is the meaning of the second line. Okay. Now, we will call RT plus 1 as the set of basis returns. So what is basis returns? Basis returns mean the set of returns that are most fundamental to the economy. You can view them as individual stock returns. Okay? So there are, say, n individual stock returns. Okay? And I am using notation RT plus 1. Okay? And this is because the current time is T, and the return is going to be realized in the future. 현재 시간이 T이고 실제로 리턴이 알려지는 시기는 다음 피리어드죠. T plus 1. Therefore, I'm going to use RT plus 1. In other words, for the investor that is in time T, okay, so the current time is T, future time is T plus 1. So the investor who is at time T, for that investor, this information, this return that is going to be realized at T plus 1 is not known. Okay? 무슨 말이냐면 리턴은 다음 날에 일어나는 리턴이기 때문에 타임 T에 있는 인베스터들한테는 알려져 있지가 않아요. 즉, in other words, this information is not included in time T information set. Okay? But it is going to be included in today's information set. Any trading strategy ZT and payoff XT that depend on time T information set belong to FT. Because when you form a trading strategy should be known at ZT, at time T. 무슨 말이냐면 어떤 트레이딩 스트래티지를 짤 때는 미래를 보고 할 수 없잖아요. 따라서 타임 T까지 알려져 있는 인포메이션들만 가지고 트레이딩 스트래티지를 만들어야 되는 거예요. Therefore, this trading strategy should be included in time T information set, but not known in the previous day's information set. Any random variable that realizes at time T belongs to FT. Okay? In other words, say ZT is the temperature at time T. Temperature day by day is a random variable. 그날의 온도는 랜덤하게 결정되잖아요. But that is known already today. Although it was a random variable from the perspective of yesterday, it is known today. Therefore, ZT is known FT. So from the perspective of FT, ZT is just a constant. From FT's perspective, it is constant. But ZT is a random. T-1에서 봤을 때는 ZT는 랜덤이에요. Okay? Now, we will define based on the conditional information set FT. WT is set of all possible portfolio weights. And we will define XT as set of all possible payoffs spent by RT, or set of all possible payoffs from the portfolio. 즉 무슨 말이냐? You can use information at time T. 시간 T에 있는 information을 이용해서 포트폴리오를 짤 수 있죠. You can make a portfolio. 그 다음에 FT에 있는 인포메이션으로 나온 포트폴리오 리턴은 t 플러스 1m선만 리얼라이즈가 되니까 time t plus 1 subscript가 있는 거예요. In other words, these portfolio realizations are not known at time t, so it is a random variable, but it's going to be realized in the next period at time t plus 1. 그 다음에 next fxt plus 1, 0 is the set of payoffs spent by the information at time t0. Okay? So what is the difference between this and that? Okay? The first one is a dynamic strategy because portfolio weights WT changes over time. It is going to be based on the information that is known at time t. So it is dynamic. Whereas xt plus 1, 0 or w, this w is a constant. It is a constant because it belongs to information ft0. So this is a static strategy. 무슨 말이냐? xt0에 있는 포트폴리오들은 static, 정적인 스트래티지에 의한 포트폴리오 페이오프들입니다. 즉 오늘 포트폴리오를 딱 정하고 포트폴리오 웨이트를 절대 변하지 않아요. 하지만 그 위에 있는 포트폴리오는 동적 포트폴리오죠. 왜냐하면 WT changes over time. 그러면 매일 포트폴리오 웨이트가 변하게 됩니다. In that sense, XT plus 1 includes what is called the managed portfolios. Managed portfolios. In other words, you change portfolio weights over time. You manage the portfolio. Portfolio whose weights in n assets depend on the information set available at time t. So xt plus 1 is not spent by RT using only ft0. Okay. 즉 xt plus 1은 static 포트폴리오가 아니라 managed 포트폴리오, 그날 포트폴리오 초이스를 하는 페이오프이게 됩니다. Okay. From now on, I will use this notation. Okay, so whenever I have expectation like this, and this is the expectation taken with respect to F0 information set. What's the meaning of that? This is the usual unconditional information. I'm sorry, unconditional expectation. Whereas this means conditional expectation using the information that is known up to time t. 즉, 이 conditioning information은 언제 제일 중요하냐면 when is conditioning information the most important? When we want to calculate the expectations. What is conditional expectation? Given all the information today, what is the expected return tomorrow? What is the expected temperature tomorrow? What is the expected value tomorrow? Okay? That is conditional expectation. 즉, conditional expectation이라고 하면 뭘 말하느냐? FT information set. 오늘 주어져 있는 인포메이션을 모두 이용해 가지고 내일에 대한 예측을 할 때가 conditional expectation이라고 합니다. 즉, 리턴을 추정하거나 주가를 추정하거나 아니면 일기예보 같은 것도 다 conditional expectation이라고 볼 수 있겠죠. Now, the conditional expectation is defined as following. Okay, so this conditional expectation of some random variable yt plus 1. Yt plus 1 can be anything. It can be temperature. It can be something that's going to be realized tomorrow, like stock prices or stock returns. Is based on, so this conditional expectation is going to be some variable that is known at time t, okay, that is going to minimize the square distance in an integral sense. Okay? 즉 무슨 말이냐? 내일 일어나는 베리어블에 대해서 스퀘어 루트 에러를 미니마이즈 해주는 타임 t 인포메이션에 근거한 베리어블이 곧 컨디셔널 expectation이에요. conditional expectation. In other words, a conditional expectation of yt plus 1 is the best guess of yt plus 1 given ft when yt hat is a linear function of all time t variables. Conditional expectations defines the conditional linear regressions. Okay. The usual unconditional expectation, 보통 얘기하는 평균, unconditional expectation is simply some constant okay, that is going to minimize square distance okay, from that constant. Okay. And this is the last point is very important. Okay. Expectation of yt plus 1 is a constant. Okay. So say there can be average stock price, average temperature, and so on. While conditional expectation of yt plus 1 is a random variable that is going to realize in time t. So this is the random variable. It's a random variable in the sense that it is not known yesterday. It is not in yesterday's information set, but it is going to be in today's information set. Some useful and very important results. The first one is so-called the law of iterated expectations. 한국말로는 여기에 맞는 단어가 없어요. 그래서 law of iterated expectation 혹은 LIE라고 외우셔야 됩니다. Okay? Law of iterated expectations. This is very important. Okay? Suppose your information set is included in a bigger information set. Okay? So when does that happen? So FT can be information set of all investors. Everything that investors know at time t. Whereas GT then is going to be the subset of that, meaning information known to only a few investors. Some subset, okay? When that is the case, expectation that is taken in a much finer information set, and when you take that, when you take the expectation of that conditional expectation, then it's going to be same as simply taking the expectation with respect to G. So let's take a look at this simple example. Suppose conditional expectation is given like this, right? So I told you conditional expectation is a time t random variable. So it has time t subscript in it. It is a time t random variable. Okay. Then what is the unconditional expectation? According to the law of iterated expectations. Okay, the two will be the same. Okay, now mu to the yth power is a constant, so it will just come out. B is also constant, it will come out. And expectation of BT. Okay. Note that the converse doesn't hold. Okay. The converse meaning that unconditional expectation of the conditional expectation is not the same as the conditional expectation. That is not true. Okay? This is because this thing here is simply a constant, therefore it becomes a constant, whereas on the right hand side this is a time t random variable. Okay, another useful relationship is this. So if this holds for all possible z's, then it has to be the case that this is 0. Okay? So this is similar to what you will learn in the mathematics class. Okay? If there is some variable x times y equals 0 for all y, then x should be 0, right? It is very similar to that. Okay. Again, law of iterated expectations, LIE, 아주 중요합니다. The most important thing. One interesting thing is the conditional covariance. This is very important because finance theory is all about covariances. So on the left-hand side, what is this? Unconditional covariance. On the right-hand side, that is expressed in terms of conditional covariances, right? This is conditional, that is conditional, and that is conditional. Okay, so you can actually prove it. Okay, okay, try. What is the hint? Hint is add and subtract. Okay, add and subtract here. Okay, then you will find that. Okay, more generally, this thing holds, right? So the conditional covariance given in GT information set that is coarse than FT can be expressed in terms of average of the conditional covariance plus covariance between the conditional mean. Okay? 무슨 말인지 아시겠어요? 즉 무슨 말이냐? 코베리언스 X와 Y의 코베리언스는 X와 Y의 컨디셔널 코베리언스의 에버리지랑 그냥 똑같지가 않고 여기 엑스트라 텀이 붙어야 되는 거예요. 엑스트라 텀. What is that extra term? The covariance between the conditional means. Okay? Covariance between the conditional means. Okay? Now let's talk about some expected utility and microeconomic theories. So assume there's a utility function ut. And we say that an agent is indifferent between x and y if the value of the utility functions are the same. So we say that the agents are indifferent. And when ux is greater than uy, utility of x is greater than utility of y, we say the agent prefers x to y. 즉 utility가 agent의 preference를 매저하는 함수입니다. Now, We will assume the following choice under certainty. Agents prefer lottery. Lottery can be anything. lottery 복권이죠, 복권. 복권 뭐 주식도 복권이고 모든 financial asset 다 복권이라고 우리 가정할 겁니다. Agents prefer lottery or payoff that delivers a higher expectation of utility. So suppose two lotteries, LA and LB, with random payoffs XA and XB. Now, if the distribution of X is known, we can calculate expected value of X. And then we can also calculate the expected value of utility based on XA, and also the expected value of utility based on XB. Then the agent will strictly prefer LA to LB. And we typically assume that UX is monotonically increasing in X and twice differentiable. This is just a technical assumption. 별로 중요한 assumption은 아니에요. 기술적인 이유로 우리가 가정을 할 겁니다. And the arguments of U, the utility function U, can be anything: wealth, consumption, payoff, and so on. This inequality is very, very important. Okay? What's called the Jensen's inequality? Jensen의 inequality, Jensen의 부등식, Jensen's inequality. Now, when function f is concave, what's the meaning of concave function? This is the concave function, right? When function f is concave, okay, concave function is if and only if for all a between 1 and 0 and any a and b, for any a and b, so this is FA and that is FB. For any values of A and B. Now, what is on the left-hand side is what is called a linear combination. 한국말로 하면 내분. Linear combination between FA and FE. What is it? That is the straight line that is a straight line between FA and FB. Okay. That straight line is below. The straight line is below. So what is this? This is that straight line is below the actual function value. Okay. So this is going to be F lambda A plus 1 minus lambda B. Okay. So whenever this point, this is above this point here, this point is the linear combination between the two. Okay. Then we call the function f is concave based on the Jensen's inequality. Okay. In other words, when f is twice differentiable, then concavity implies that f double prime is a negative number. And it follows that for random variable z, we have the following. Okay? Expected value of the function. This is very important again. Expected value of some concave transformation. Some concave transformation of the random variable. Average of that is always greater. I'm sorry, always smaller than the average of the function value. Functional value of the average. Okay. This is very, very important property. Jensen's inequality. I would say the most important concept in today's lecture. Now, let's talk about risk aversion. An agent is risk averse if the agent dislikes all zero mean risk at all levels of wealth. That is for all level of wealth W0 and risk X. But the risk, when I say risk, it's a random variable. It's a random variable. Okay? It's random. X is random. Okay? So in other words, what is X? X is some random variable. So it's going to be realized based on, so there's a mean. On average, it's going to be E of X. But the realization is somewhere here. Okay. Okay. Now the investor, the agent is gonna, it doesn't like it. So agent has the current wealth W, and then agent is gonna have mean zero and payoff. So on average, X is gonna be zero, but if things are good, X is going to be $100. When things are bad, X is going to be negative $100. 한국말로 하면 여러분이 어떤 W0라는 돈을 가지고 있어요. 거기에 when things are good, 좋게 장이 좋으면 X가 100만 원이 되고 장이 나쁘면 X가 마이너스 100만 원이 되는 거예요. 즉 여러분의 웰스가 있는데 여러분의 재산이 있는데 운이 좋으면 재산이 올라가고 운이 좋으면 재산이 떨어지는 거예요. 근데 if you're risk averse, you are going to prefer no risk counterpart of that than the risky counterpart. That's the meaning of risk averse. In other words, this is like, which one are you going to prefer? $100 for sure versus $150 and $50 with equal probabilities. Okay? Which one are you going to prefer? If you're risk averse, then you're going to prefer $100. An agent is risk averse if and only if the agent's utility function is concave. In other words, the secondary derivative is negative number. Now, it is sometimes easier to define the following coefficients. The coefficient of absolute risk aversion, therefore it's ARA, is defined in the following way. So a well-known absolute risk aversion utility function is the following, where gamma is the absolute risk aversion. This is the absolute risk aversion. Now, the relative risk aversion is defined in the following way. So why is it called elasticity of margin utility? What is elasticity? Elasticity is basically percentage change with respect to percentage change, right? Or if you take log, if you do this, then that's actually margin utility. Okay, so Okay, so in this sense, it's the elasticity of marginal utility. So what is absolute risk aversion? Let's get a little bit deeper. It measures the dollar amount that the decision maker would pay to avoid an actual fair gain. Okay. So what is the fair gain? So this is the random outcome. Okay. So this is the case where you get C. So your outcome is C plus epsilon. Okay. So it's either, I don't know, C plus 100 or C minus 100, something like that. So based on random realization of epsilons, your payoff, your consumption is going to be C plus 100 or C minus 100. In that case, your expected utility, okay, your expected utility is going to be like that. And of course, you're risk averse. You don't like this uncertainty. So you want some discount in your level of consumption, but you want it for sure. There's no expectation. It's a constant utility. Okay? Now, so this is what's called a certainty equivalence. So this negative half of, this is the certainty equivalence. So you are willing to give up this much, okay, to get the to get an outcome that is there's no randomness. And absolute risk aversion measures the per unit dollar gamble variance. Okay? So it's a fair compensation per unit dollar of the variance. Okay? How do you show that? You just expand the utility function using the Taylor's expansion up to the second order. Okay, and then you can obtain the formula here. Okay, and then comes the relative risk aversion. Relative risk aversion is just a scaled version of the absolute risk aversion. So it's the amount as a fraction of consumption that the agent is willing to pay to avoid a fair gamble per unit of variance of the gamble expressed as a fraction of consumption. Okay? So the only difference is this. Okay. So in a relative risk aversion setting, you want to make it as a fraction of the consumption. Okay. Now, next important concept is log normal random variable. Okay. So when the log of random variable x, okay, so there's random variable x, and you take the log of it. x라는 랜덤 베리어블이 있고요. 그거에 로그를 취했을 때 그 로그를 취한 베리어블이 normally distributed 됐을 때. In other words, when the log of the random variable x is normally distributed, okay, in other words, log of x is a random normal random variable with mean m and standard deviation of sigma. We call the random variable is log normally distributed. So it returns IID. What is the IID? That's independent, identical, distributed. Okay. Independent and identically distributed. So if returns IID with finite variance in small intervals, then compounding returns will converge to a log normal random variable. We will see that later in class. Commonly used to model stock returns because of some nice mathematical properties. What is the most nice, the nicest properties of the log normal random variable is the following. Okay. In other words, I'm sorry. In other words,
say, was it Z or? Okay, so suppose random variable Z is log normal. In other words, log of Z is mean 0 and, okay, then we can calculate Z, expected value of Z, and also variance of Z as well. Now, let's just do it for, okay, so to make it easier, suppose it's a standard normal random variable, okay? For this case, E of Z is if you use the let's call it let's suppose Z is a normal random variable, okay? And X is a e to the Z. Then log X is a standard normal random variable. Therefore, X is a log normal variable, right? Okay. So Z is the standard random variable, standard normal random variable, and X is the e to the Z, and then X is called the log normal. Now, then we can calculate expected value of X. Okay. How do we do that? Expected value of e to the Z. Okay. This is okay. And is this right? Yes, this is right. And this is the same as this, right? Okay. Therefore, okay. And what is this? What is this? It is a simple integral of the density function. This should be one. Okay, so this is, okay, and you can do similarly. Okay, so therefore, expected value of Z is, okay, and you can similarly do the calculation of this as well. Okay, more generally, when Z is a normal random variable with mean M and standard deviation of sigma squared, then this is simply E expected value of Z plus a half of variance of Z, which is E to the M plus a half of sigma squared, okay? This is a very, very important result, okay? In other words, therefore, log of e to the z. So this is e to the z is basically x is basically m plus a half of sigma squared. What is m? That is the average of log of x plus a half of variance of log of x. Very, very important result that is known. Okay. In summary, we have reviewed the important things, important mathematical and economical results that is necessary to understand asset pricing theory. Okay. What are they? Conditional information, law of iterated expectations. What else? Jensen's inequality, absolute and relative risk aversion, and lastly, the mean of the log normal random variable.